Now we're ready to look at universal generalization and existential generalization. This is where we have something like this. If we've reached a point in our proof, or maybe we have P of X, and we know that P is true for all X values in the domain, then we can add back the universal quantifier. If we reach something like this, say Q of A, and we know that Q is true for A, which is in our domain, but maybe it's not necessarily true for every value in the domain, well then we can add in the existential quantifier. Right? So let's look at a problem. Sorry, this should be this. So if we ignore the quantifiers, basically have, if A implies B and we have A, then we get B. Right? So our hypotheses. Now we want to strip the quantifiers here. Does it matter which order we do these in? Well, no, because this is universal, this is universal. Okay? So whatever specific value I may choose for one of these, it still works for the other one. In fact, we won't even use a specific constant. We'll still just say X. That'd be fine in this case. So A of X implies B of X. And then we also have A of X. And so this is from 1, this from 2, and both of these are universal instantiation. Okay? And now, given that we know A of X implies B of X, and we have A of X, we can get B of X. So this is 3, 4, modus ponens. And now the question is, can we generalize? Well, we knew here that we said this relationship is true for every X in the domain. And we also had this, which was true for every X in the domain. So yes, we can generalize to this. This would be 5 and universal generalization. If we'd had a mixture like universal and existential, then I wouldn't necessarily know this was true. Okay, but this is universal, so I can extend from there. What we'll do in our next video is look at some specific problems. So we'll take some word problems, set those up, and then solve those.